Welcome to today's Explainer. Okay, we are jumping straight into a genuinely groundbreaking idea today, one that could completely change where we look for alien life in the universe. For decades, we've been staring up at the stars with a very specific and honestly a pretty limited picture in our heads of where life could actually exist. But today, we're exploring a fascinating scientific framework that flips that old script entirely. It's called the Circumplanetary Habitability Advantage Hypothesis. We're going to unpack exactly what that big term means, why it matters, and how it could completely redefine our place in the cosmos.
So here's our agenda for today. We'll start with the old view of life, move into the moon advantage hypothesis, figure out why moons beat planets, talk about testing and falsifying the theory, and finally wrap up with the real-world space implications.
All right, starting things off with Section 1, the old view of life.
So for decades, astronomers have essentially been hunting for the perfect planet, acting like massive solitary space rocks are the absolute only places life could possibly survive. I mean, think about every sci-fi movie or space documentary you've ever seen, right? The holy grail of astronomy is almost always finding an Earth 2.0. We have spent billions of dollars building massive telescopes just to hunt for lonely, Earth-sized planets orbiting stars exactly like our sun. We've kind of just assumed that because life happened on a planet here, well, it must only happen on planets everywhere else. You've probably heard of the Goldilocks zone back in science class. It's that specific region around a star that isn't too hot so your water doesn't boil away, and it isn't too cold so your water doesn't freeze into solid ice. It has to be, just right. But notice the intense bias there? The entire concept is built around how much heat a planet receives directly from a star. We've always made the planet itself the main character in the search for water and life.
Which brings us to Section 2, the moon advantage hypothesis. Let's see what happens when we shift our focus.
This brings us to a really fascinating hypothesis brought forward by researcher, inventor, and author Kevin L. Brown. He is challenging the most basic assumptions of astronomy with a straightforward but totally radical claim. He proposes that if you take a water-rich planet and you compare it to a water-rich, rocky moon, the moon might actually be the much better bet for finding life.
The crucial point here is that being a moon around a giant planet isn't some sort of disadvantage. It's actually a massive cosmic upgrade for habitability. Let's break down that big term, circumplanetary habitability advantage. Circumplanetary literally just means being in orbit around a planet. So, Kevin L. Brown's hypothesis basically states that being a moon tucked into the orbit of a giant gas planet gives you unique sources of energy and chemistry that a lonely, solitary planet just doesn't get to have.
So, moving to Section 3, why moons beat planets. Let's dig into the actual mechanics here.
When we compare a comparable water-rich planet to a water-rich, rock-bearing moon, the major scientific takeaway is pretty simple. The moons get a double dose of energy. Think about it. A solitary planet is kind of like someone sitting by a campfire. If the fire goes out, or if they just move too far away from it, they freeze. Their only source of heat is that star. But a moon? A moon gets heat from the star, plus it gets heat from its giant host planet. Because the gas giant's gravity is just so incredibly strong, it physically stretches and pulls the moon as it orbits. It's exactly like rapidly squeezing a rubber ball in your hand over and over again. The friction makes that ball warm up from the inside out.
This constant squeezing creates what we call tidal heating. And when you combine that deep warmth with a rocky bottom to provide essential minerals, you create this perfect, warm, nutrient-rich soup for life. It is literally a complete life support system. The tidal heating keeps oceans of liquid water warm under the ice, even if the moon is incredibly far away from its sun. The rocky core provides the basic chemical building blocks. And on top of all that, giant gas planets usually have massive magnetic fields that act like a giant umbrella, shielding the little moon from deadly space radiation. It's a highly dynamic, constantly churning environment. Honestly, it's exactly what you want if you're trying to spark life.
All right, Section 4, testing and falsifying the theory, because every good scientific idea needs to be tested.
We can actually validate Brown's theory using modern telescopes. Or we could falsify it if planets consistently win the data race. To validate the heat advantage, we basically need to detect excess heat radiating off distant moons, exomoons as we call them. If we look out there and find that all these moons are just frozen solid chunks of ice, well, the theory takes a huge hit. Next up, biosignatures. We need to find markers of life, things like specific gases spraying out of the moon's geysers. But if solitary planets end up having way more of these life markers than the moons do, that's a falsification parameter. Finally, water stability.
We have to prove liquid water is actually sloshing around under there, and that it hasn't completely boiled away from too much tidal squeezing, which could actually cause sterilizing toxic volcanoes.
The actual validation process follows 3 really simple steps, giving astronomers a clear checklist for the next generation of space telescopes. First, we find the giant planets, the big gas giants like Jupiter or Saturn, but, out in other solar systems. Second, we look incredibly closely at them to spot the tiny shadows or the little gravitational tugs of rocky, water-rich moons orbiting them. And third, and this is where super advanced instruments come into play, we analyze the light passing through the geysers or atmospheres of those moons to look for biological markers.
And remember, the hallmark of great science is falsifiability. Science isn't just about trying to be right, it's about making a prediction that is bold enough to actually be tested. If we spend the next 50 years scanning the cosmos and find that lonely, solitary planets consistently have more complex chemistry and life markers than these squeezed moons, then the circumplanetary habitability advantage hypothesis fails. And honestly, that's totally okay. That is exactly how we learn and push our understanding forward.
Finally, let's look at Section 5, Real-World Space Implications. Why does all of this matter to us right now? The real-world implications here are absolutely huge. It means we need to stop just looking for Earth 2.0 and start pointing our best equipment at the moons of giant gas planets. We literally have to rewrite the rules on how we schedule valuable telescope time. We also have to completely redraw the map of the Goldilocks zone because, well, tidal heating means a moon can be way outside the traditional warm zone and still have liquid oceans. This vastly increases the sheer number of places in the universe where life could exist. And maybe most importantly, it tells us to look closer to home. It tells us that moons like Jupiter's Europa and Saturn's Enceladus, right here in our very own solar system, might actually be the absolute best places to find out we aren't alone.
So it leaves us with a pretty profound thought to wrap up today's explainer. What if the alien life we've been endlessly searching for has been hiding on a moon this whole time? Thanks to the Circumplanetary Habitability Advantage hypothesis by researcher, inventor, and author Kevin L. Brown, we have a brilliant new lens through which to view the universe. The next time you look up at the night sky, don't just wonder about the planets. Wonder about the moons.